How's everybody doing tonight? A few things before we get started. Once again, I'm gonna ask your indulgence for when I am preparing class when I'm setting the arena up. Please wait until I'm done before you come up and ask me questions. It'll all generally start pacing, or I'll sit here, then feel free to come up. Talk to me about that. To those who have just placed themselves in this course, my email address is shown down. Do not expect seeing me and ask me questions in person. After class, I really need time to prepare for the 7 o'clock class. So I don't mind if people come and ask me questions or right after lecture, that it's at 658 I'm going to have to stop answering questions so that I can prepare for the next class. Please don't be offended. If I say come back after 7 o'clock class, but I have responsibility that 7 o'clock people to be ready for their class. Let's see. Oh, all right. So on Friday, probably I'm going to start to chapter 4, which won't be on the exam, I might add, but we're going to start to talk about cyclic compounds, and models are going to be very, very important on Friday. If you have a set of models, I recommend you bring them, and make a 6-membered ring, a cyclohexane ring. Make one of those, because when I play with that extensively, my reuse ask or my office hours on Saturday 9 to 11 as usual. Practice exams coming out Friday, and noon on the course website. Quick poll. How many people here are in the 7 o'clock class, enrolled 7 o'clock class? Okay, I just want to know. Interesting. Okay. Anything you want to talk about before we get started? No. Okay. So tonight I'm going to spend hopefully most of the time, talking about a very important concept, the concept of resonance forms and resonance in organic orginium. But before that, I had so many questions about radical halogenation. I do want to clear one thing up. So the first example of radical halogenation that we talked about was this one. And I had a methyl group to it. Now there are a lot of different possible products. So let's count them. In fact, there are 12,345 different possible products. So these 3 hydrogens on a methyl group, they're always equivalent by symmetry, so that will give rise to one product. We'll call those hydrogens type A. Then this one, that tertiary hydrogen, that's a unique replacement event by a chlorine, will give yet another product. We'll call it B. And then these 4, 1, 2, 3, 4 have the same relationship to the rest of the molecule. So replacement of one of these 4,234, that would give yet another unique product. So we'll call those C. And these 4, 1, 2, 3, 4 also have the same relationship structurally to the rest of the molecules, or call those the replacement of any one of those 4 will give it yet another unique product. And finally, there's these 2, which are unique, and they'll give rise to a 5th possible product. We'll call it E. So the concept is in a molecule that's unsymmetrical, that's an even, this one has some symmetry to it. You're going to get the number of possible manochlorination products that corresponds to the number of structurally different kinds of carbon-hydrogen bonds that are present. So that's pretty good exercise. Draw for yourself some alkanes. And look at it and decide for yourself how many different kinds of hydrogen are present. I will teach you something about structure. Okay. With that behind us, let's get into the topic of the evening. So other than learning about mechanisms this quarter, what a mechanism is, the next most important concept is probably the concept of resonance forms, or resonance in organic originometry. So what are resonance forms? Done with us, right? So resonance forms are different electronic representations of a molecule or ion. They have the same sigma bond structure, but they have a different arrangement of multiple bonds and non-bonding electron pairs. Different arrangements of multiple bonds, non-bonding electron pairs, and in single electrons. So this last category, single electron, that would only apply to radicals. Resonance forms, different electronic representations of molecule or ion, same sigma bond structure, different arrangements of multiple bonds, non-bonding pairs, and or single electrons. Resonance forms tell us a lot of important things. They're going to tell us something about the stabilities of ions, and they're going to tell us something about where reactivity can occur, where nucleophilic or electrophilic or radical reactivity can occur in a given molecule or ion. Okay. That'd be what I'm going to start with, is we're going to consider a cation called the alcation, but before that I want to talk about cations in general. So we haven't talked about these yet. Too much detail, but a carbocation is just a compound that's got a positive charge on a carbon. Sometimes a carbocation ion is referred to as a carbonium. On these two terms mean the same thing. And unfortunately, your book uses both of these terms interchangeably, but essentially they just refer to a carbon or a molecule that's got a positive charge on a carbon, that's all. So if we take a really simple carbocation like methyl counterions, what is the electronic structure of that species? Well, what we've got is carbon has 3 electron pairs emanating from it. So that means that carbon is sp2 hybridized. And its bond angles are about 120 degrees. More importantly, because carbon will use an sp to hybridized orbital bond to this hydrogen, sp2 to that one, sp2 to that one. There's a leftover carbon 2p orbital emanating from that carbon atom. And that's what you need to know to be able to understand what I'm going to talk about next. All right, so consider the following cation. That one right there, my script's got a special name that's called LOL-cation. That's one way to represent it. Now to represent this molecule, or this ion with orbitals, you have to understand what I just talked about there. So there's going to be two p orbitals overlapping here. There's going to be an empty p orbital on that carbon. So just to differentiate these, I'm going to call that carbon 1, carbon 2, and carbon 3 to look at that from an orbital point of view. Drawing the p orbitals. So the 3 carbons and the 3 orbitals are in the plane of the drawing surface, and I've just drawn the rest of the hybrid. All right, so since there's a double bond between carbons 1 and 2, carbon 1, carbon 2, carbon 3, we will indicate that those two lines, remember what those mean, they use these orbitals in the double bond, they're actually cutting or overlapping. But we don't draw them like that because that would be difficult to picture the rest of the molecule. Instead, we indicate the pi bond with a line, a dotted line, or a straight line between the lobes, the orbitals. Okay, so this picture, this horrible picture corresponds to that drawing the double bond between 1 and 2. Got an empty carbon pure orbital on carbon 3. Now, we can also represent the allo-cation differently. So I'm going to start over here. This cation can also be represented with the double bond in a different place. We have a 3 orbital system across 3 carbons that contains a total of 2 electrons. Those 2 electrons are in the pi bond in this structure between carbons 1 and 2. So it's a 3 orbital system containing 2 electrons and are all contiguous. We can equally draw an electronic representation where in fact the pi bond is located between carbons 2 and 3 and the plus charge is over here on carbon 1. Put that in these 2 are different electronic representations of that ion. These 2 are resonance forms. Now to translate this back to this kind of structure look like this. Plus charge over here on carbon 1. These 2 are resonance forms and we indicate their relationship as resonance forms with a special double-headed arrow. You're only going to see this double-headed arrow and 2 in one place. That's not an equilibrium arrow. This indicates that 2 structures are resonance forms. 1430. Now, the question then becomes, well, if the cation has this electronic representation as now electronic representation, what is it really? Is it this, or is it that the answer is the allo-cation? It's not this, and it's not that it's something in between. It's a resonance hybrid. Everybody knows what a flower hybrid is. It's a combination between two flowers. It's not really one or the other. It's something between 2 same thing of the resonance hybrid. We can indicate what a resonance hybrid looks like with a structure that contains dotted lines. And the resonance hybrid of the alkane ion might be represented like this. So what does that telling me? It's telling me there's a double bond character. It's telling me there's 3 electrons, or there's 2 electrons across 3 orbitals. So we're not really sure if the double bond is location, so that the double one can be located here, can be located here. So we brought double bond, we put a plus charge in the middle. It's not on that middle carbon. Actually, it's just on the whole system as a +1 charge. Now it's not that important to be able to draw resonance hybrid from a series of resonance structures. That's not important, the concept is, but being able to draw these is not important. What is important is being able to draw all the resonance forms of a molecule, or ion, when you have its conventional structure. So if you're given a structure like this, it's important that you understand that the client can be represented by this, by that. So what resonance forms tell us? One very important thing they tell us is where electron density lies in a molecule. Where's the electron density? And that tells us something about reactivity. So looking at these 2 resonance forms, what we see is that there's a lot of positive charge character on the 2 end carbons 1 and 3, but there's none on carbon 2, because in the resonance forms, we see a plus charge on carbon 1, plus charge on carbon 3. So because cations, carbocations in particular, are electrophiles, we would expect this cation to react with electrophiles, with nucleophiles rather, on the end carbons, but not in the middle. So because we now know something about the electronic distribution in the molecule, we can predict something about its reactivity. Okay, that was an important concept. Are there questions before I go on? Yes. Repeat the last one. So one thing the resonance forms tell us is where a positive charge character and negative charge character exists. That's important because positive charge character is electrophilic character and negative charge character is a nucleophilic character. So if you look at the 2 resonance forms where the positive charge is located, That's where you can expect a nucleophile to combine with, and when it tells us the alkentinas. A nucleophile will combine with it at the 1 carbon or the 3 carbon that is the end carbons, but not in the middle. Okay, so what are some rules? Unfortunately, I got to roll this down. What are some rules regarding the drawing of resonance forms? Okay, before we get any further into it, here are some things that are important. Oh, all resonance forms of a given molecule or ion have the same net charge note in the allo. Can I do for you the net charge on both forms was plus one of your drawing resonance forms, and you got different net charges on forms some drum. Relative positions of the atoms and the resonance forms do not change, i.e., they do not move. What does this mean? What it means is the sigma bond structure does not change. So in drawing resonance forms, sigma bonds never break. They're always in the same place. Notice in the alpha canon, all I moved was the pi bond. That's all moved around. Structures with the maximum number of atoms possessing an octet of electrons contribute most to the resonance hybrid structure. So resonance forms where the maximum number of atoms have electrons around them, those are the most important of the resonance forms. Charges plus charges minus charges are best accommodated on atoms, the appropriate electronegativity characteristics. What that means is negative charges are best accommodated on highly electronegative atoms, as opposed to not very electronegative balance. We'll go through an example of this shortly. And then finally, less separation of charge is more important than greater separation of charge. Let me illustrate this because this is a very important point. You can take any pi bond now this cheap university. I had 5 of these things, now there's 1. All right, let's consider something very simple, just ethylene, a pi bond here, that's an electron pair. We can draw a resonance form of any double bond by just moving the electrons in the pi bond out to one of the carbons, or there's one of those curved arrows. It indicates movement of 2 electrons. So I've taken the electrons and the pi bond and put them on this carbon, the resonance form that results a plus on the left-hand carbon and a minus on the right-hand carbon, the resonance form of this. However, these generally do not constitute what are called valid resonance forms. So I'm going to put in parentheses, not a valid form. And say print, so put in quotes, not a valid form. What does that mean? A valid form contributes significantly to the structure of the hybrid. And a form that's not valid doesn't contribute significantly. So any double bond can always be written like this. However, remember 5 states, less separation of charge is more important and greater separation of charge. This one has greater separation of charge. Because of this one, there are no net charges on atoms. On this one, there are 2 net 2 charges on atoms. So this kind of resonance of just isolated double bonds. Generally, it's not important, and we don't even draw those as resonance forms. Yes, I did. I just did, right. So for example, that's gonna fall off, That hasn't got a follow-up. But even in cases where we're talking about valid resonance forms, the octet rule can be violated. That's actually a really good question. Let's look at that. Look at another catalan and its resonance forms, but one that doesn't involve pi bonds. Let's look at this camera. Now, resonance form of this canon exists, where the non-bonding pair on nitrogen is participating in resonance. So we take this non-bonding pair and we allow it to be a pi bond between C and N, and that can be accommodated because carbon's got an empty orbital, then that results in a resonance form that looks like this. So in these to this resonance form, that carbon doesn't have an octet. In this resonance form, all the atoms have an octet. So going back to 1-2, rule number 3 structures, the maximum number of atoms possessing octet of electrons contribute the most hybrid structure. That means this will contribute to the hybrid structure more than that one, but they're both valid resonance forms. I think I answered. Yours personally. I think that's what you're asking. Okay, let's take a look at resonance. Structures involving anions. All right, consider the following anion. And I'm going to draw in the non-bonding pairs because they will be important. Minus I, so there's a carbanion cabana, and compound or carbon atoms got negative charge on it. Resonance form exists, whereby this electron pair on carbon can become a pi bond between the 2 carbons. But if I were to do that, then this carbon would have too many bonds to it. So something's got to break that's going to be a pi bond. So the pi bond can break and become a non-binding pair on the oxygen. That resonance form will look like this. And now oxygen's got 3 non-bonding pairs and negative charge. Now these two looking at the rules, call this one a call this one be calling the rules, which one would contribute more to the hybrid A or B? They have always very good AI system that got choice and a negative charge on carbon or some negative charge on oxygen. Oxygen is more electronegative than carbon, so it's able to take the negative charge character better than it would be if it was on a carbon. So B contributes more to the hybrid, but and B are both valid resonance structures. What does this tell us about nucleophilic reactivity and a number of the atoms 123? Where does the nucleophilic reactivity lie in this carbon ion? On which atoms? Ah, that's a sure. Volunteer. Go ahead. That's right, so in the resonance forms, we see there's negative charge on carbon 1 and on the oxygen, which is atom 3. So that the ion will react as a nucleophile and either carbon 1 or the oxygen atom. But not that carbon. Capture. Let's do a few more. So here's a species called a carboxylate anion. Carboxylate anion. You're gonna study the originometry of these in detail and come first week, I think in ORGM 140. See carboxylate anion. There's a resonance form of this, and it's going to involve non-bonding pair on this oxygen and that adjacent pi bond. Resonance form can be drawn by allowing what the electron pair to become a double bond between carbon in the lower oxygen, breaking the pi bond to the upper oxygen, allowing it to reside now on the upper oxygen is a third electron pair, and you get a resonance form. Let's do a few more. Here's a species called a carboxylate anion. Carboxylate anion, you're gonna study the originometry of these in detail and come first week, I think in ORGM 40. See carboxylate anion. There's a resonance form of us, and it's going to involve non-bonding pair on this oxygen and that adjacent pi bond. Resonance form can be drawn by allowing what the electron pair to become a double bond between carbon and the lower oxygen, breaking the pi bond to the upper oxygen, allowing it to reside now on the upper oxygen as a third electron pair, and you get a resonance form. Okay, so there are the two valid resonance forms of the carboxylate anion. Question: where will this ion react as a nucleophile on what atoms? Where will the daggett where's the nucleophilic character in this ion on both oxygen atoms, but not that carbon? So it can react as a nucleophile in either place. Let's do something a little bit harder. This one I'm gonna let you do at your seats. Okay, so this one's a guy and this is carbonate, and I am reasoning by analogy and what you learned so far. Draw all the resonance forms of carbonate anion, go to it. Okay, a lot of crosstalk. Let me see by show of hands how many people have what they think are all the resonance forms. Show of hands. Ooh, that's a lot. That's good. All right, volunteer, how many resonance forms are there? There are 3, good. That one. And there is. That one. How many people got these 3 hands? Okay, good question. Where does the nucleophilic character in carbonate anion lie? All 3 oxygens, but not the central carbon atom. Okay, questions so far? Very good. Please. We sing as is not just the same thing rotated. Yeah, it is, but in drawing resonance forms. When you draw the molecule and its sigma bond structure, and you do not rotate it, you don't move it in the plane to the drawing surface. So while they appear to be the same, if let's say you had an oxygen 17 label that was an isotope oxygen 17. Now you'd see they're different, or at least 2 of them would be different. In drawing resonance forms, don't move the atoms around on a page, drop one way, and only move non-bonding electron pairs and ions. Let's try some cations. Okay, there's a carbocation ion, draw the resonance forms of this carbocation ion. Okay, how many people have what they think is a complete set of resonance forms hands? That's enough paperwork. Okay, let me have a volunteer. How many total resonance forms are there? Can be a volunteer. How many? There are not 6. There are not 5. How many? There are not for 12 now. There are 3. There are 3 reasons. That one. And there's that one. if I had drawn these two hydrogens, and that might have influenced your answer. So a carbon that's fully substituted, that's sp3 hybridized, bonded to 4 other atoms, never involved in resonance. Why? Because it doesn't have a non-binding pair, and it doesn't have a pi bond go into it. So this carbon number 2, it can never be involved in resonance. Next volunteer. I want to know, where does positive charge character lie in this molecule? Volunteer. Go ahead. Call the numbers. And that's right, for positive charge character lies at the positions where there are positive charges and the 3 resonance forms. Now would be carbons 1, 3, and 5. That's where you can expect a nucleophile to react. And not on carbons 2, 4, and 6. Yes. In order. That's a reasonable assumption. Let's do another one. Okay, I'll give you only a minute to do this one. Draw the resonance forms of that cation. Okay, how many total resonance forms are there? Resonance forms are there? There are 2. Call this carbon 123, where we're in this ion, this positive charge character line. What atoms? 1 and 3 on the end carbons, but not in the middle. Question was, where does positive charge character lie? And the answer is, it's a carbons 1 and 3, because that's where the plus charges are. In the resonance forms. So that's where nucleophile will react. Yes. Because I moved this pi bond, which is moving an electron away from that atom. Oh yeah, thank you. So far, we've only talked about canions and anions. Radicals also have resonance forms. So this radical is called LL radical. To draw the resonance forms of radicals, we do not move 2 electrons at a time, we move 1 electron at a time, and we use one of these kind of half-headed arrows. Remember, that means moving to 1 electron. To draw the resonance form of this, we would draw like that. Like that, and that resonance form would be. Call that carbon 1, carbon 2, carbon 3. Where does radical character in this molecule lie? Where does the radical character lie in carbons 1 and 3, and not at carbon 2? Good. Okay, so what we see is that resonance forms can tell us about the reactivity of ions, tells us where there's nucleophilic character and anions. It tells us where there's electrophilic character and chynes. It tells us where there's radical reactivity and organic free radicals. What else do resonance forms tell us? Well, we saw this. They indicate where the electron density is located. Atom with high electron density is nucleophilic, and of low electron density is electrophilic. They also indicate something about the stabilities of ions. So has anybody heard the saying that nature abhors a vacuum? You heard that. You might have heard that one of your science classes, that's a Diet Coke, that there's definitely a diet. So nature also abhors a charge. So in ions, when a charge is highly localized on one atom, which means the charge is not spread around by resonance forms, that highly localized charge means it's a pretty reactive ion, and it has relatively low stability compared to an ion where the charge is spread out by resonance. So in this particular case, we see the plus charges spread out over 5 atoms. Those 5 that plus charges is heavily resonance stabilized, and so it's a pretty stabilized ion. So highly localized charge is a plus or minus is not as stabilizing as the localized charge with the localized charges. It's charged character that's spread around by resonance. And these two are pretty much the same. Now, let me come back to one more concept. Do you remember how we talked about the order of radical stability? What's the order of radical stability? It's not tertiary. It is primary. This is a primary radical. However, the primary radical is much more stable than any tertiary radical. Why? Because the radical character is spread around to 3 atoms by resonance. This is essentially a 3-electron system spread over 3 carbons. Resonance is a highly stabilizing factor when it's applied to molecules or ions. What generally, not always, but generally more resonance forms means you can spread a charge out to more atoms. Greater stabilization. Okay, we'll see you Friday, where we will cover the orogenical value chain, synthesis basics, and some review of hyperconjugation. Okay, see you next time.